everyone. So thank you for staying up to this time for this demo after the conference. So my name is Rodrigo Ventura. I am faculty at Instituto Técnico, also researcher at Instituto of Robotics of Garcis. Together with me is CoBot. She's a PhD student at IST, working with us, and also was involved in this demo, but she had to leave earlier. Jesse Pujar is not here right now. So what I want to show you is two lines of research on the application domain of space robotics. And we have here two robots that illustrate that demo those lines of research. So one line of research is focused on the orbital robotics, and we are motivated by the fact that in the International Space Station, there is a limit on the crew size, so we have a maximum of 6 astronauts. It will be interesting to have robots to collaborate with the astronauts to help them. Also, in a similar context, we know that there is this project of the Deep Space Gateway for helping the road to Mars and using the Moon as a test bed. In this Deep Space Gateway space station that is being designed for the orbiting the Moon, there will be a long period of time where it will not be crewed, and so it will be necessary to have robotic technology to perform logistics such as take out equipment from a spacecraft and so on. And so we designed an autonomous robot for helping in those two contexts. So collaboration with astronauts and also autonomous transportation of material. And so what we have here is the Space CoBot. Space CoBot, it's a prototype. Space CoBot means a collaborative robot for in space. And so the design is similar to what we have drones here on Earth, but with a big difference. While the multi-rotors here, they have the propellers in parallel position, because most of the energy is used to counterbalance the gravity. Here, in space, in orbit, we don't have gravity, and so we can exploit the direction of propellers because we don't need to spend that effort. So what we did was to obtain what is the optimal orientation of propellers so that we can have a more maneuverable vehicle. Okay? And so, here on Earth, we cannot test completely this vehicle. So what I did was this setup where you have these rings that allow the robot to freely rotate. So what I'm going to show now is attitude control, which is I will give a set point, and it will control the orientation of the robot for that set point using the propellers. Okay? We have already done a little bit more than that, which is use this platform, and you can see we have the chance to see that on the videos. Is that using an air-bearing table, we have this platform floating horizontally, so we can get 5 degrees of freedom, 2 for position and 3 for the orientation. Okay, so here on Earth is the best that we can do, otherwise only on parabolic flights. Okay, so the motion might be a little bit windy, but that's because the rings do some perturbation. So this setup allows us to validate stabilization in altitudes, but of course because of the rings of the gimbal, it's not that faithful when we do motion. So I can rotate. So what I'm doing now is I'm changing the set point of the altitude, and it's rotated on the z-axis, and I can also rotate it in the other axis. And of course I can combine any one of these factors. Also, for safety, it's not the propellers are not spinning at maximum speed, and so that's why it needs to be also to be slower. Also, there is a concern in the space station because of the noise, and so we limit the propeller speed to a certain point. Of course, this is the back control. You can measure how much can be run, and it will go back to the set point. we are doing a set point, and we are also capable of doing smooth trajectories, and we can see that in between the we have done. So this concerns the line of research on orbital robotics. We have also research on the problem of what happens when we have a robot such as this one grasping an object. We have interest on doing manufacturing in space, so we are limited with the current long technology, what we can launch to space, and we are very much interested. And we have MIT Portugal seed project on that, on studying methods to do assembly of large structures in orbit, and we also have interest on doing manufacturing in space, which is using this kind of free-fly robots to do 3D printing of structures in space. Of course, the propellers, this only works with air. It's designed for the ISS, but from the theoretical point of view, it's just a matter, if you want to go outside of the station to space, it's just a matter of changing the thrusters. So all of the mathematics of the dynamics and the control is essentially the same of using thrusters or using the propellers. Okay, so let's go now for the other one of research. This one concerns autonomous robots. This is completely different. Is the problem of teleoperating a robot. So this robot that you see is here is not for space, so it was designed for search and rescue missions, and we are spinning off that research to the area of space. Okay, so it was designed to be for rescue missions, and it is continuously teleoperated. And the problem that we're facing, that we are researching in the line research, is when we are right now looking to the robot, I give you a joystick, it's very easy to operate because you are watching the robot. But this robot is designed for search and rescue operations where the operator is not seeing the robot all the time. And this is very, it causes multiple challenges because it's very easily the robot can be stuck in a certain environment and you are not aware of that because you only see the image from the camera and it might get an angle or get an orientation that might be dangerous for the robot and you are not aware of that. And so having all of the information inside the screen, it's too much. And so we are looking on the methods of offloading information from the computer screen to our hands, okay? And so we have designed haptic devices that transmit this kind of information to your hands. In particular, what we are going to show are two devices. So one is an attitude device. So what happens is that as you change the orientation of the robot, this device will change its orientation. It's not for control, it's for feeling. So you put your hand over there, and as the robot changes orientation, you feel in your hand also changing and gives in a very intuitive way the attitude of the robot. The second device is a vibrating glove, which is somewhere over there. Okay, it's here, and this is to address the problem of being stuck. So we have in previous missions on search and rescue trials, we observed very frequently that when the robot gets stuck somewhere, also you are not seeing the body of the robot, so as easily as you are rotating the robot, it can be stuck in an obstacle. The operator gets very easily very confused. Okay, so what I did was comparing data from the sensors of a laser rangefinder and odometry, we were able to detect that robot is stuck, okay, and make this glove vibrate, which means that the operator feels on his hand very quickly these states. In fact, we are detecting two kinds of states. One is stuck, which is the robot has the wheels moving, but they are sleeping and the robot is in the same place. And the sliding, which is sort of the opposite, which is the wheels are static and the robot is sliding on a surface. These are two different conditions. We have two different vibration patterns, and that way the operator can see it. How do we evaluate this kind of methods? We do systematic user studies, so we recruit volunteers that do systematic trials in the same conditions, so that we can get statistical significance of whether these kind of devices improve the efficiency of the task. Okay. Do you want to demo something? The robot. Sure. Okay. We also have here so we have also here a 3D glasses. So this is used to exploit using augmented reality the problem of. So first you have a higher immersiveness on the area if you use these 3D glasses. You have, so with these glasses, you have two displays for two eyes. We have two cameras in the front of the robot, okay? And so this gives you a perception of depth through stereo. So using these glasses, you can perceive objects at not very distance, but at a few meters from the robot, and you can feel, you can see which is closer to you and which is farther away, and this improves the situation awareness that you have. Also, as Ruth rotates her head, this camera also rotates, which means that you are operating the robot. If you want to look to the side, you just need to move your head, and the camera will also rotate. Okay? So this allows to decouple the orientation of the robot from the orientation of what you want to see. If you want to see something on your side, you just need to rotate your head, and the camera will rotate. Okay? So all of these are techniques to improve the situational awareness that the operator has of the robot. Okay? As I mentioned, this line of research started in search and rescue missions, and we are spinning off this for robotic exploration and planetary exploration. And we applied an experiment to the AMAD 20 analog mission to Mars that is being organized by the Austrian Space Forum. It was going to happen this November. It will be postponed for the next November. And so it's an analog mission to Mars where you have, during 1 month, in isolation, a team of analog astronauts, and we will have these astronauts using our experiment. So our experiment is this box over here, this suitcase, which contains the computer and the devices. We are not using this robot in that experiment. We are collaborating with the University of Graz that provides the rubber. And so we will use the analog astronauts, not only for the experiments, in these controlled experiments that we can see, we can assess in a systematic way the gain of efficiency of using these devices, but we also be involved in cascade experiments, which is, so this analog mission has a story, which is we have a base in Mars, we have analog astronauts that want to go to some hot spot to study something, and they send the robot before to get data from the environment. And we are going to use our teleoperation console to operate this rover to do these initial experiments before the astronauts go over there. Okay? So this is basically what I want to show. Thank you so much. If you have any question, I'm open to questions, of course.
Estou, mas agora a interação mesmo. Oh, sim.